Welcome to today's session of Astro Adda. We have speakers from the Astronomical Society of India who are coming here to speak to you on various astronomy topics, and we have these sessions with possibility of students picking up some quantitative explorations as a follow-up after this. And when we say supermassive black holes, it just excites everyone from school to college to senior researching people, and we are very fortunate that we to take us through this supermassive black hole walkthrough. We have with us Dr. Yogesh Wagadekar from the National Center for Radio Astrophysics, Pune, and using the GMRT, they have done some very interesting observations in connections with supermassive black holes, and I'm sure in our walkthrough um, we will have Yogesh share with us these aspects. Um, I just want to tell the participants who are there that as we go along, you can use the chat window for putting any questions that you have, but the speaker would be able to notice the questions only after the talk is ended, and so we will have a lot of time for questions at that time. Yogesh, we are really very happy that you are here to take us through this. I will hand over to you. I'm going to put your screen share also. It's visible now to the viewers. And thank you for
Yes. Thank
agreeing.
you for the warm welcome, Ratnashri. It's a pleasure for me to speak here. Am I audible to clearly?
Yes, yes, yes.
Yes. Okay. Today, I'm going to talk to you about supermassive black holes, which are located at the centers of most galaxies. My name is Yogesh Wagadekar, and I work at the National Center for Radio Astrophysics in Pune. NCRA, as we are called, is a center of the Tata Institute of Fundamental Research, and we operate today the largest meter wave radio telescope in the world, which is called as the GMRT. And I'm sharing with you now a screenshot from today's Hindu newspaper, wherein it says that GMRT has been accorded the prestigious IEEE milestone status. This is a very, very rare honor from an international organization, which was just announced yesterday for the GMRT. And the other two recipients of this honor from India are Jagdish Chandra Bose for his work on radio waves, and Professor C.V. Raman for his discovery of the Raman effect. And GMRT is the third. So we are really honored that a telescope facility that we run in India is being recognized in the company of greats like Jagdish Chandra Bose and C.V. Raman. Okay, now coming back to the topic of today, we are going to talk about black holes. So first we will talk about what are black holes and why we are interested in looking for them. Then during the later part of the talk, I will talk about how supermassive black holes can be searched for and how supermassive black holes help us understand how galaxies form and evolve. And throughout, we will look at each of these questions from a very simple physical perspective. People who do research in each of these fields work in very, very complex, intricate, difficult ideas involving black holes. But since this is a beginner audience, I'm only going to talk about the very basic aspects. If you have some questions about what I speak, as well as somewhat more advanced aspects of black holes, we'll definitely be able to take them at the end of the talk. Before we get started, I'd like to give a 3-minute introduction to the 13 billion year history of the universe. We now believe that the universe began about 13.7 billion years ago in a massive explosion, which we call as the Big Bang. At the time of the Big Bang, the universe was so small and so hot that even atoms could not form. But as the universe expanded, it cooled, and eventually a stage was reached where the protons and electrons and so on that we know of today began to form. And after a certain amount of time, about 400,000 years, 4 lakh years, the universe had cooled enough for protons and electrons to come together. Protons and electrons, when they come together, they form the simplest atom of all, which is the hydrogen atom. And once hydrogen atoms form, then the history of the universe can proceed in a different way. One of the things that happens is hydrogen atoms begin to attract each other through gravity, and larger clouds of hydrogen get formed when the hydrogen atoms coalesce due to their gravity. At this time, there is no light coming out of the universe except the light of the Big Bang, which is, of course, propagating through the universe. But at some point, the hydrogen clouds collapse to form stars. And when they form stars, the first stars are formed about 400 million years after the Big Bang. The universe lights up. And these stars, of course, then collect to form gigantic agglomerations of stars, which we call galaxies. Around stars, we also begin to form planets. And these planets, of course, like our own solar system, there are hundreds of, there are few planets around almost every star. And we know of billions and billions of planets we believe now exist in our galaxy, and thousands of them have been directly discovered. Now, the black holes that we are going to talk about today primarily are the supermassive black holes, which we believe are formed at the centers of galaxies. But before we go in that direction, we need to see what a black hole really is and what's the basic concept of a black hole. Suppose we take a planet of a fixed mass m, okay, and start squeezing it to smaller and smaller sizes. As you know that if the mass is fixed, the surface gravity of a planet gets stronger as you make the planet smaller and smaller. The surface gravity is proportional to the inverse radius square. So if you make the planet of mass m, squeeze it to half its current size, the surface gravity will become 4 times. So as you go smaller and smaller and smaller, eventually a stage is reached that the surface gravity is so high that nothing, not even light, which goes at the highest speed, can escape from it. So effectively, if you understand the concept of escape velocity, then the escape velocity from the surface of that planet will become greater than the speed of light. And well, before this, the planet itself will collapse into nothingness and form a black hole. So what is a black hole? A black hole is an object whose surface gravity is so high that nothing can escape from its clutches, not even light. So if it emits some light, we can never see it because it simply does not allow the light that has been emitted to escape. Now, over what radius is this happening? So there is an important quantity which we refer to as the Schwarzschild radius, which is given by this number 2gm by c square. The capital G is Newton's gravitational constant, and m is the mass of the object, and c is the speed of light, right? So if you plug in the numbers, so if you now ask a very simple question, I want to take a planet like the Earth and I want to convert it into a black hole. Obviously, you will have to reduce its size continually till that happens. To do that, you need to turn the Earth into an object the size of a grape, okay, which is about, let's say, 1 or 2 centimeters in diameter, right? Now, what about the sun? Suppose you take the sun and you want to squeeze it down to a size that it turns into a black hole. For the sun, you'll have to squeeze it down to a Schwarzschild radius of about 3 kilometers, right? And why is that? Remember here, the Schwarzschild radius expression is equal to 2gm by c square. This tells you that the Schwarzschild radius is directly proportional to the mass. So if there are two objects, one has double the mass of the other, then the high mass object will have a Schwarzschild radius, which is double the Schwarzschild radius of the less massive object. So the sun, it turns out, is about 1,000,000 times more massive than the Earth. And therefore, its Schwarzschild radius is not the size of a grape, but it is much larger, about 3 kilometers. So what you see in the picture below here, those of you who have been to Mumbai may recognize this. The bridge that you see in the foreground is the Bandra-Worli sea link. And what you see in the buildings in the background are roughly, let's say, 5 or 6 kilometers across. So if you could take the sun and squeeze it down to the size of this region of southern Mumbai, then it would turn into a black hole. Now we come to the fact that there are two fundamental types of black holes. Okay, black holes with masses of a few solar masses are well understood and are now directly detected in gravitational wave events. How do these black holes form? The most massive stars that are formed in our galaxy and in other galaxies have an end of life in which they end up in a massive supernova explosion. When they die in such a supernova explosion, they leave behind a small black hole. By small, one means a black hole with a mass a few times the mass of the sun. Black holes are inherently simple objects characterized by just three numbers: their mass, their spin, and their charge. By spin, one means how quickly they're turning around, what is their angular momentum. But in this talk, I'm going to only focus about the mass. So this is a picture of a supernova remnant. So when a massive star explodes as a supernova, it leaves behind a very beautiful structure, which we refer to as a supernova remnant. It can be seen with optical telescopes. It can also be seen with radio telescopes like the GMRT, and it can also sometimes be seen in X-rays. So our galaxy is full. There are millions of stellar mass black holes, dead stars, which are scattered across the entire disk of our Milky Way galaxy. And these stars, these are just remnants, these stellar mass black holes are remnants of massive stars that have gone through their entire lifetime and have finally exploded as a supernova. But there is another kind of black hole, and that is the focus of the talk today. We believe that there are something called supermassive black holes with masses of 1,000,000 to a few billion times the mass of the sun, which live at the centers of galaxies. Okay, we understand what they are and where they're found, how massive they are, and so on. Okay, but we don't understand today exactly where they come from, when they formed, how they grew in size, and so on. These are all areas of active research in extragalactic astrophysics. So here's a picture of a galaxy. It's one of the well-known nearby bright galaxies. It's referred to as the Sombrero Hat Galaxy, and it houses a black hole at its center which has a mass about 1 billion times the mass of our sun. So this is an example of a supermassive black hole at the center of a galaxy. We now will take a little detour and talk about a specific class of objects, quasars, or more generally active galactic nuclei. So in 1963, an astronomer in the United States, Martin Schmidt, found a very, very interesting radio source. So what he was looking systematically at very bright radio sources that had been found with the early radio surveys done at Cambridge University in the United Kingdom. And he was looking at an object called 3C273. So this is object number 273 in the third Cambridge catalog. And when he looked for at the position of that radio source, he found exactly at that position a 13th magnitude star. Star is with quotes because it turned out that this isn't a star at all. But what he found was very remarkable, that when he looked at its spectrum, initially the spectrum was very mysterious, but eventually he realized that the spectrum corresponds to a highly redshifted object. Okay. Now, as the universe expands, objects which are further and further away from us are moving away from us at higher and higher speeds and show higher and higher redshifts. So this enormous redshift of 16% of the speed of light was discovered for this object. And this obviously meant that this was the most distant object known at that time. But because it was so bright, or relatively bright in the night sky, it was quickly realized that it must be enormously luminous. So it turns out quasars, or active galactic nuclei, or which are a kind of active galactic nuclei, are the most luminous objects in the universe, often outshining an entire galaxy. So the immediate question came to mind: how are these quasars powered? Okay, and as we shall see in a minute, this was the first compelling argument for the presence of supermassive black holes at the center of galaxies. Martin Schmidt became very famous. He appeared on the cover of Time magazine, and so that's his picture from Time. And on the left is a more recent picture of his. And at the bottom is the spectrum of 3C273 that he had obtained with an optical telescope in California. Okay, so what are these quasars? Quasars are objects that are extremely luminous, okay, very often extremely luminous in all bands, all the way from radio through optical through X-rays. And they're bright because they have a very, very hot disk of material, which we shall encounter in a minute again, at the center, which is going around the supermassive black hole. And from the supermassive black hole, often, not always, often you have jets of material which are streaming out at very high speeds, close to the speed of light, and forming these very large structures, which we refer to as lobes, which are most easily seen in the radio bands. So this is a nearby radio galaxy called Cygnus A, with its gigantic radio lobes stretching very large distances beyond the optical extent of the galaxy. Okay, so then people started, okay, quasars are so luminous, how are they powered? That was the simple question that was asked. So the first possibility was, could they be powered by nuclear reactions like those that power stars? You know that the sun is powered by fusion reaction that converts hydrogen to helium continuously and gives out a lot of energy. If you look at the energy stored in the radio halo and the radio lobes of a quasar, that is a very large amount of energy, about 10 raised to 54 joules. If you use Einstein's equation, E is equal to mc square, This much energy corresponds to a mass of about 10 million suns. It turns out that nuclear fusion reactions have an efficiency of only about 1%. So if you sort of burn enough material, or you fuse enough material uh, to generate the energy output of a quasar, you would be left behind with a waste mass of about 1 billion suns. And we know that rapid brightness variations of typical quasars already told us that a quasar, or the region from which the quasar emission is coming, is only as large as our solar system, which is a very, very tiny fraction of the size of a typical galaxy. Right? But so it's very difficult to pack in 10 million suns into our solar system. We only have one, remember. Okay, but if you think of the gravitational potential energy of 1 billion suns, which gets compressed into the solar system, that will release an energy of 10 raised to 55 joules, which is more than enough to give you the 10 raised to 54 joules that you observe in the radio. So this is now a famous statement by Donald Lynden Bell, a famous astrophysicist. Evidently, although our aim was to produce a model based on nuclear fuel, we have ended up with a model which has produced more than enough energy by gravitational contraction. The nuclear fuel has ended as an irrelevance. So now we believe that quasar engines are supermassive black holes that are releasing energy because they're swallowing the surrounding gas and stars. And as the gas and stars falls into the black hole, it releases an enormous amount of energy, which you see in the form of a quasar. The long jets that I mentioned for radio galaxies are seen in many, many, many radio galaxies. And we know that those jets are so long and they're so collimated and they're so coherent that they must remember their ejection direction for a long time. And this would argue against energy sources based on many objects. So you could claim, if you claim that there are many supernovae going off at the center of our galaxy, right? Then it would be hard to say that there is only one jet that comes out from all of them, because they would tend to drive energy in a much more isotropic manner, which means equal energy output in different directions. But as we know, jets are very, very narrow, and they're often focused in a particular direction. So this suggests that whatever it is that is powering the quasar are rotating gyroscopes or rotating black holes. Right? Jets have also been found to move at very high speeds, close to the speed of light. Okay, and this implies that their engines are as small as black holes. Okay, so supermassive black holes, we now believe, are the engines that power quasars. And their huge luminosities and tiny sizes can be explained if they are powered by black holes with masses of somewhere between 1 million to a few billion times the mass of the sun. It turns out that gas near the black hole settles into a hot disk and then releases gravitational energy as it falls into the black hole. And there are magnetic fields which play an important role for the ejected jets and maintain their collimation along the rotation axis. So this is our modern picture of what is going on at the center of all active galactic nuclei. There is that black circle at the center, which is your singularity or your supermassive black hole. Matter that is infalling is shown in the form of a glowing disk of gas, dust, which is infalling into the black hole. What does happen is that relativistic jets, okay, jets of particles and radiation are blasted out at at near light speed in a direction perpendicular to the disk of the galaxy. And this accretion disk of supermassive gas and dust is continuously whirling around the black hole at immense speeds. And as it whirls around, it gets heated as it comes closer and closer to the black hole. And that releases an enormous amount of light, electromagnetic radiation, which you can see on Earth in the form of emission, in the form of X-rays uh, and optical radiation, ultraviolet radiation, and so on. So this is our picture of what a black hole or a supermassive black hole actually is, and how it gets heated up, how it releases energy at all frequencies. So, how do you feed a quasar? One simple way is a galaxy merger. Okay, whenever there is a galaxy collision, galaxies merge like this, and if each of them has a supermassive black hole, then these supermassive black holes will also encounter a lot of gas which has been dumped into the center by the merger, and eventually these two black holes are going to circle around each other, come closer and closer together, and eventually merge. Okay, they go faster and faster, and they form a bigger supermassive black hole, which is formed at the center of the merged galaxy. Okay, this is a simulation. This is not a real image. It takes a very long time for this to happen, but this was done as a computer simulation just to illustrate how black holes merge and how their accretion disks also get disrupted and form a new accretion disk around the merged black hole. So we now believe the overall picture that we have for supermassive black holes. But for many years, there was no direct evidence that these massive black holes actually exist. And so for the rest of the talk, we're going to talk mostly about how we observe these supermassive black holes, okay, and how we study them today. The quasars or active galactic nuclei in the universe were very active about 3 or 4 billion years after the Big Bang, which means about, say, 10 billion years before the present time. Quasars were there, active galaxies were there in most big galaxies. But if you look at the universe today, you see that position now, almost all the quasars have now switched off. Okay, they're no longer active, but there should still be the black holes sitting at the centers of galaxies, including in nearby galaxies, including in our own. So the question is, how do we find these supermassive black holes? The search for supermassive black holes has been driven largely by optical telescopes. And here is a telescope. Here is a photograph of telescopes located on the peak of a volcano in Hawaii, known as Mauna Kea. And there are two telescopes at top right, which are the twin Keck telescopes. And we are going to look at the results from those two telescopes to understand how they were used to study the supermassive black hole at the center of the Milky Way galaxy. So, a telescope has its most powerful instrument in the form of a spectrograph, which is basically a way, it's simple spectrograph is shown in this picture, wherein you basically have the light coming in from the left. There's a collimating lens, and then the light is dispersed through a prism, and then it is focused onto an electronic detector, and then recorded and studied at later times. So what happens when you look at a center of a galaxy through a spectrograph? So what happens is that if you are looking at the center of the galaxy, on one side of the black hole, the gas and stars will be moving towards you. And on the other side of the black hole, they'll be going away from you, depending on the direction of rotation of the accretion disk around the black hole, right? Or even beyond the accretion disk, what you see in the form of gas and stars that are feeling the gravity of the black hole. Now, these objects will then show up in the spectrum either as a slight blue shift or as a red shift. And by measuring how much by measuring the speed of rotation of gas at different distances from the black hole, one can estimate what is the mass of the black hole, right? And there you get in the spectrum, the rotation through the spectrum, you get the rotation speed. You see a slight blue shift on one side, and you see a slight red shift on the other side. And this technique was used to measure the black hole mass at the center of the Andromeda galaxy. And it turned out that is about 40 million times the mass of the sun. So how is this actually done? Let us do a little bit of maths in order to understand this. So the distance to the Andromeda galaxy is about 2.5 into 10 raised to 6 light years. Okay. And we have observed a rotation velocity through the spectrum that we obtained of about 160 kilometers per second at a radius of 1 arc second. Now, as the gas is going around the galaxy, we need to balance the centripetal acceleration with the gravity from the supermassive black hole. And mv square over r is the centripetal force, and gmm over r square is, of course, the gravity. And if you just rearrange this equation, you get an expression for capital M, which is v square r over g, where m, of course, is the mass of the supermassive black hole. Small m is the mass of the orbiting star or the gas cloud or whatever it is. G is the gravitational constant. If you plug in numbers for all of these, then you get a mass for the Andromeda galaxy of 22 times 10 raised to 6 solar masses. This is an underestimate because it does not include the effects of projection or random velocities. So the projection effect is depending on whether the rotation is face on or edge on or more edge on with respect to our viewing angle. You will tend to underestimate the speed v that you measure, that 160 kilometers per second that you measured, and therefore it becomes difficult to get the exact mass, but you can get a minimum mass of 22 million times the mass of the sun. And so that's how we discovered that there are black holes at the centers of most massive galaxies. Okay, here's another example, NGC 3115, with a black hole mass of 1 billion times the mass of the sun. Okay. The second major advance was driven by the launch of the Hubble Space Telescope in 1990. And in the last 30 years, the Hubble has enabled us to get a real ringside view of what is going on in the centers of galaxies. So Hubble was able to look at a nearby elliptical galaxy, M87, okay, and they were able to see the gas disk near its nucleus, and they were able to obtain a spectrum. And the same technique that we described earlier, you measure the rotation curve and find out what is the red shift and the blue shift. And from the difference in the Doppler shifts, one can calculate that the disk in this case rotates at almost 600 kilometers per second. And this implies a black hole mass of about 2.5 billion times the mass of the sun. Here's another example. with the Space Telescope Imaging Spectrograph, where they went and studied the nucleus of a galaxy called M84. That too has a very massive black hole of about 1 billion times the mass of the sun. Here's two more examples. Okay, and of course, in our own galaxy, there is a black hole somewhere between 2 to 5 million times the mass of the sun. So have we discovered black holes in galactic nuclei? Have we seen them directly? I'm going to come to that in a few minutes. But the answer is most probably, because any other alternative will require us to become very unphysical with the arguments. But this absolute proof requires that we see velocities of almost the speed of light near the surface of the black hole. So as you go closer and closer to the black hole, the object should move faster and faster. We've seen some evidence of that in the observations of a kind of galaxy known as Seyfert galaxies. And X-ray observations have shown that very, very wide spectral lines are showing that the objects there are moving at about 100,000 kilometers per second, which is 1/3 of the speed of light. So in the 1990s, the question was asked, can we measure the motion of individual stars? Okay. And the answer was yes. And that was possible for our own galaxy. And that led to the award of the Physics Nobel Prize this year to three people: Roger Penrose for theoretical work on black holes, but also to Richard Genzel and Andrea Ghez, two astronomers who used optical telescopes to study the motions of stars at the center of the Milky Way galaxy. Richard Genzel worked mostly with the European VLT, and Andrea Ghez worked extensively with the Keck telescope in Hawaii, which I talked about a few minutes ago. A very, very important engineering innovation was critical to making this possible. Okay, so what you're seeing, the blurred picture that you see now, is gradually sharpening up. Okay, the first picture is blurred because the Earth's atmosphere is not very stable, and because of turbulence in the Earth's atmosphere, the sharpness of images is lost. This is a problem that plagues all ground-based optical telescopes. But for some telescopes, a technology known as adaptive optics has been implemented, which corrects for the distortions made by the Earth's atmosphere and sharpens the image. What you see, that little square at the center of the image, which is zoomed in at bottom right, you see individual stars that are located very close to the Milky Way galaxy. Without adaptive optics, you will not be able to see those stars individually. But with the adaptive optics turned on, those stars come into sharp focus and can be followed. Their motion around the black hole can be followed for individual stars. And this was what was done by Genzel and Ghez. And this is what earned them the Nobel Prize in Physics this year. So what you see here in this picture are stars moving around. The little star-shaped object at the center is the supermassive black hole. Okay. And there are lots of stars which are moving around under the gravitational influence of that particular black hole. And there is one object which is circled, shown by this yellow ellipse that you see near, vertical ellipse that you see near the center, is a star known as S02. And this star has been found to go around the center of our galaxy in 15 years' time. So it completes one orbit in 15 years. To place this in context, the sun takes about 200 million years to go around our galaxy once. But this particular star is so close to the center of our galaxy that it goes around the center of our galaxy once in 15 years. And by measuring the velocity with which it moves when it is at different distances from the center of the Milky Way, which is indicated by that star-shaped object at the center, we are able to calculate what is the mass of the supermassive black hole that is sitting at the center. And this is the number that was measured by these two people by painstaking observations, which are still going on over the last 25 years. Okay, so now let us, towards the last 10 minutes, talk a bit about why is this important? Why are we trying to study black holes at the centers of galaxies? It turns out that the evolution of a black hole at the center of the galaxy is connected to the evolution of the galaxy as a whole. Galaxies have two main components. One is the disk, which is a flat structure that we have in the Milky Way, for example. But there is a more spheroidal structure, a more three-dimensional structure, which is referred to as the bulge, which is usually located at the centers of galaxies. Turns out it was discovered very early that this bulgeless galaxy, there was a galaxy called M33, which is a spiral galaxy nearby. It does not seem to contain a black hole. But that is because it turns out also that it does not contain a bulge. And then people started asking the question, is the formation of the bulge related to the formation of the black hole? Is it true that bigger black holes reside in galaxies with bigger bulges, and so on? So they went and measured the sizes or the masses of bulges in galaxies, and then they went and measured the masses of the supermassive black holes sitting at the center of that galaxy. And what they found was, yes, there was a correlation. For example, in M33, the stars are moving at only 21 kilometers per second, and any black hole there must be less massive than about 1500 times the mass of the sun, which is not very large at all. So research has shown that every galaxy that contains a bulge component, here you see that bulge component. This is a galaxy that is almost 100% bulge. Okay, there's hardly a disk visible. This contains a black hole. And if the bulge is big and massive, then the black hole at the center will also be big and massive. If the bulge doesn't exist for a particular galaxy like M33, then it will be very difficult, if not impossible, to detect a black hole at the center because it will have very low mass. Okay, so here's another galaxy. This is what we refer to as an edge-on galaxy. It's got a disk, and that central protrusion at the center, that circular thing at the center, is the bulge of the galaxy. So this galaxy will have a black hole. This is another galaxy which does not seem to show any bulge. And if there's no bulge, then there's no black hole. And this is just a quantitative way of showing a correlation between the luminosity of the bulge and the mass of the black hole. So we found that bigger black holes live in bigger galaxy bulges. And we also found that bigger black holes live in bulges in which the stars move faster. Okay. So these two things are correlated with each other. So it turns out that the formation of bulges and the growth of their black holes, when they're shown like quasars, happen together. So understanding the evolution of quasars will help us understand the growth, not only the growth of the black holes which powered them, but also the growth of the bulges of the galaxies in which they are sitting. So this is important because this allows us a handle on galaxy evolution by essentially unifying two major areas of extragalactic research: the study of quasars or active galactic nuclei and the study of galaxy formation. In the last 5 minutes, I will like to focus on another very interesting observation, which was done a few years ago. It was announced about a couple of years back, 1.5 years back. Uh, this is a very interesting observation done with radio telescopes located at different locations. So, what you see in the picture, there's a telescope at the South Pole. There is a telescope called ALMA in Chile in South America. There is the Large Millimeter Telescope in Mexico, the Submillimeter Telescope in the United States, the Submillimeter Array in Hawaii, along with the James Clerk Maxwell Telescope, and a 30-meter IRAM telescope located in Europe. So at radio frequencies, observations were actually made in April 2017. Okay, this time they observed not the Milky Way center, but the nearby galaxy whose mass they wanted to measure. We'll come to that in a minute. The data were recorded with independent radio telescopes. Okay, normally when you want to combine data with different radio telescopes, what you see here as V1T and V2T are voltages that have been induced in a telescope, in a radio receiver, by radio waves that are propagating from the astronomical source. Depending on the direction from where the source is located, there will be a delay in the arrival of the radio wave to its center at each of the antenna, and the voltages that are received at each of these receivers are combined in a specific way in a computer or an electronic machine known as a correlator, and the correlator outputs are then used to construct the image of whatever object you're looking at through the radio telescope. So this was not possible in real time because these telescopes were very far away. But all these telescopes, the one in South America, the Atacama Large Millimeter Array, as well as the South Pole Telescope, everybody recorded their data at the same time while pointing at the same object. And then those recorded data were stored on hard disks, and those hard disks were transported, for example, from the South Pole. Just to take the hard disks out of the South Pole, you have to wait for summer to start again so that you can reach the telescope and so on. So it's a very difficult exercise. They gathered 0.5 ton of hard disks, which were needed to hold all the observations. They were transported together, connected to a correlator, and the observations were then analyzed. And what they found was something quite remarkable. They were able to get a direct photograph in radio light of the black hole that is located at the center of the M87 galaxy. This is a galaxy at the center of Virgo. We've seen earlier pictures of that during this talk. And this galaxy has a very, very massive black hole, about 5 billion times the mass of the sun. Okay, it is very far away. It's 55 million light years away. But by using this large telescope, which is known as the Event Horizon Telescope, formed of radio telescopes located on different continents, it became possible to obtain for the first time a direct image of the black hole. Now, how big is the black hole? Okay. For context, what is shown there is the sun with the orbit of Pluto shown as a circle. Okay. So it is not much bigger than the radius of the black hole is not much bigger than the solar system, exactly as we had suspected. This is an extremely difficult observation. It took about 5 years to plan. It took a couple of years to execute correctly. And then It took a couple of years to analyze the data and to come up with this image. And it involved a large team of about 100 astronomers who made this discovery. So this is, I think, a seminal advance in the study of supermassive black holes in galaxies, where we have a direct image of the black hole at the center of M87. The same research team from the Event Horizon Telescope are trying to obtain now an image in other galaxies, including our own Milky Way. So, what's the future outlook? With the present generation of technology that we have, it is possible to derive black hole masses for thousands of quasars and other active galaxies, and to probe the growth of black holes with time as the universe evolved. And this is helping us understand how galaxies, largest fundamental building blocks of the universe, have formed and evolved. I thank you for your attention, and I'm sure there must be many, many questions that come to your mind, and I will try to answer them as best I can. Thank you. I cannot hear you, Ratnashri, at all.
Oh, sorry. I was muted. Sorry.
Yeah.
Thank you, Professor
Yeah, yeah.
Yogesh, for taking us through this. I was just mentioning that there are overwhelming amount of questions, just too many. And now
Okay.
let us see how we are going to handle this. And this
Yes.
is to all the participants. Please don't put in unnecessary messages. I've lost many questions because of that. Because you see, it's not allowing me to scroll back to the very beginning. It only does some. So I have
Yes.
been archiving them in Paint.
Okay.
Meanwhile, some of the questions. So I will
Yes.
do that. And
Yeah.
well, maybe Yogesh, if you would come to the studio window. Uh,
Yes, I
okay,
have
so
opened the studio window. Yes.
yeah, I'll keep flashing these questions while I'm also working on retrieving the older questions.
Sure, sure. So you can flash. Once I finish answering a question, I'll let you know. I can see the question
Yes,
on
yes,
the
I will.
screen
I
now.
will flash the next
And
one.
then
Meanwhile,
you
I'm
can
just
flash the next one.
yes, yes.
So this is a very interesting question. What do we know about the interior of a black hole? So remember, the black hole is characterized by this radius, right? Which we refer to as the Schwarzschild radius. We can obtain information about what is happening outside of the Schwarzschild radius, because light can escape from there. We can detect it, we can study it, we can analyze it, and we can tell what's going on. But the interior of a black hole, which means within the Schwarzschild radius, we have no direct way of observing it, right? From theoretical work, we know that a black hole is really a singularity, which means it doesn't have a size. The size of the black hole itself is not the Schwarzschild radius. The size of the black hole is zero. It's like a point in geometry. Okay, it has no dimensions, zero length, zero breadth, zero height. It's gone to zero. Now, there obviously we don't understand physics as well as we would like. And there is a lot of theoretical work that is going on in trying to study black hole singularities as a theoretical problem. But as far as observational studies go, we know nothing about the interior of a black hole, because no information is available to us that is coming from the interior or from within the Schwarzschild radius of a black hole.
In this connection, I think several people were asking about wormholes, black holes,
Yes,
and
yes.
so on. So
So
maybe, yeah.
I encourage you to watch a movie called Interstellar if you are interested in these kind of problems. So the idea of a wormhole comes from the is related to the black hole in the sense that the Einstein talked of a continuum of space and time as essentially space and time are not separate; they're coupled together and manifest. I mean, they should be really thought of as one entity, which he referred to as space time. And a black hole, because it's a singularity, it has no dimensions, it represents a tear, it represents a hole in the fabric of space time. And then some people said that, okay, if the fabric of space time is broken where you have black holes, could we sort of circumvent the usual limitations that we have in traveling? For example, Einstein's theory predicts that no object, no material object, can travel at a speed greater than that of light. Okay, so some people surmised and they came up with a theoretical formulation which is known as a wormhole, which is basically like a tunnel that allows you to travel from one part of space to another part of space without being restricted by the speed of light. And that idea was explored in this movie Interstellar, wherein they sort of entered into a black hole and then they traveled through a wormhole and they exited somewhere else and they had some adventures there and then they came back. So it's a definite strong theoretical concept. Okay, it's related to the concept of a black hole. Okay, but as we said, we don't know how to build a wormhole today, and we don't even know whether it really exists. Okay.
Yeah.
Uh, can you shortly explain about trapped surface for which Roger Penrose got the Nobel Prize? Unfortunately, I don't know the answer to that question, so I'm going to have to defer that. Roger Penrose has worked on theoretical aspects of black holes, not so much supermassive black holes, which I am interested in, but mostly with stellar mass black holes and their properties. So I'm not very familiar with that question.
Yeah, actually, uh,
Okay, so this is again some things that I don't quite know. Okay. This is
okay.
an interesting question. Supermassive black holes have an enormous mass of the order billion times the solar mass. How is this enormous mass gained by the black hole, and any model to explain its evolution? Right. So one way of gaining mass is to actually keep on accreting matter, gas, stars, etc., eating them up and causing the black hole to grow. So black holes certainly do grow in that way, but we know from observations that black holes are not active all the time, which means they are not eating their surroundings all the time. And the reason for that is if there is a certain amount of material in their immediate neighborhood, they will swallow that up. But once they swallow that up, if there is no other material nearby, they have to go quiet. They are sitting there, black hole exists, it's not going anywhere, but it has nothing more to feed on. So such black holes we refer to as quiescent black holes. The Milky Way black hole is like that. The other way in which black holes can grow is something which I showed through that merger of black holes that I showed. Merger of two galaxies happens. Each galaxy has its own supermassive black hole. Then over time, the two supermassive black holes come together, they merge, and they form a bigger supermassive black hole. Now that's a very easy way of growing. So if you have 2 billion mass black holes which are merging, you will suddenly create a 2 billion mass black hole from a 1 billion mass black hole, which represents a very rapid increase in the mass of the black hole.
I think this question came when probably you were talking about uh, high luminosity
Yeah.
in connection with something else, so that it was inferred as black hole. Another question was, will every dense object, will it be a black hole or not? Maybe the two could be discussed.
Yes. So every dense object does not become a black hole. Remember, the mass has to be packed into an area smaller than the Schwarzschild radius. before it becomes a black hole. So there are other extremely dense objects in the universe, such as neutron stars and white dwarfs, etc., which have very, very high densities, but they're not black holes because their contraction due to gravity is counteracted by other forces. In the case of neutron star, by something known as neutron degeneracy pressure, and in the case of white dwarfs, by a force that is the pressure that's generated from electron degeneracy. So that's the reason they don't. So not every compact object or every dense object becomes a black hole.
And there was a question about whether very high luminosity, whether we are inferring it to be a black hole, anything to be a black hole from very high luminosity. Now the
Yes.
question has gone up, so I'm not able to flash it
Yeah, yeah. No,
again.
let me just see. There are two simultaneous conditions that need to be satisfied in order for something to be called as a black hole or a supermassive black hole. One is that the luminosity has to be very high. Okay. And the second thing has to be that the luminosity must be coming from a very small region. And how do we know it's coming from a very small region? We know it because the variability in the flux or the luminosity emitted is changing on the time scales of hours. And if it is changing on the time scales of hours, that means that if something is happening and that is creating an effect somewhere else, and that effect is manifesting within a few hours, that means that those two positions should not be separated by a distance more than a few light hours, which corresponds to the diameter of our solar system. That is why we keep saying that these supermassive black holes, okay, are very small, they're very tiny, okay, they're very massive, but they or whatever is happening in their surroundings can change on the time scales of hours, which tells you that they are very, very compact in size.
There is
This is a
this
very interesting
question.
question. Do we discover mid-range massive black holes between stellar and supermassive in recent times? Yes, there are a few good candidates. So, for example, in the last 5 or 6 years, we've made discoveries of a large number of merging black holes whose masses have been measured relatively accurately. And those merging black holes have been discovered using their gravitational wave signals. So, gravitational wave observatories like LIGO have observed the mergers of stellar mass black holes, and they've also observed the mass of the end product, or they can predict through their models the mass of the end product. And these end products are very, very massive objects, very, very massive objects by stellar black hole standards. These are referred to as intermediate black holes. The other kind of, so first of all, what's intermediate black holes? Anything with a mass between, let's say, 10 raised to 2 to 10 raised to 5 solar masses, we'll call as a intermediate black hole. So a little more than 10 raised to 2 solar masses black holes probably exist, based on the evidence from the gravitational wave black hole merger events. There are also interesting discoveries being made in black holes that are located in very, very low mass, low luminosity galaxies. Okay. And there has been a lot of recent work in the last few years that has discovered black holes with masses of order of a few times 10 raised to 4 to 10 raised to 5 solar masses, which are not really supermassive, but they are also categorized as intermediate mass black holes. So both in the centers of galaxies and in through merger events, we are finding intermediate mass black holes.
Actually, the number of questions are so
Yes,
many. I think we are going to have one more session just for the questions because
yes,
I have
yes.
extra 30 to 40 saved in a paint file from the beginning.
Right, right, right.
So
No,
we'll have.
it has always been, uh, is always the case. Black holes is a topic that is of almost universal interest. So there are
If
a
you
lot of
can give us
questions.
some time, maybe I mean next week or
Yeah,
so, just because we
yeah,
won't be
yeah,
able
yeah.
to
We
finish all
will
the
try
questions.
to
But,
take as
but
many
please,
as we can.
everybody, be rest assured, we will try and tackle all the questions. If not today, in the continuing session.
Sure, sure, sure. Right. So since light cannot escape black holes, can a tachyonic particle
Oh,
escape
sorry,
it?
sorry, sorry,
Okay.
sorry. Huh.
So this is an interesting question also. So tachyons are particles that are supposed to move at speeds greater than the speed of light. Okay. But in order to do that, you can't start with any real mass, because any object with a mass greater than zero, okay, uh, tends to have infinite inertia as it approaches the speed of light. Okay, because of that, you can't escape. It's got just too much inertia. But there are particles postulated, which are tachyons, which are always moving faster than the speed of light. But unfortunately, tachyons are not particles that we have detected yet. But you're right, if tachyons exist, then since tachyons move always at the speed faster than the speed of light, they should be able to escape from the black hole. That's true, but we don't know whether tachyons exist in the first place or not. They are a mathematical construct at the moment. Are the supermassive black holes at the center of the galaxy spinning or non-spinning? Is it definite or random each time? So for supermassive black holes, we can definitely say that they're spinning. Okay, there's no doubt about it. How do we know that? Because we know that uh, the supermassive black holes are invariably surrounded by this thin disk of material, which we refer to as the accretion disk. That accretion disk has a vast amount of angular momentum. We know that because we see those jets coming out in the perpendicular direction. And that angular momentum gets transferred onto the black hole as the material falls into the black hole. So we know for sure that supermassive black holes are spinning. We don't know that much about uh, stellar mass black holes. We don't know whether they're spinning or not, but they very likely are, because we know that almost everything in the universe, like the sun, for example, it's a normal star, but it's spinning around itself. Okay, over a period of some 27 days or so, it goes around. So there is no reason to expect that there will be black holes which are non-spinning. Spinning black holes are harder to treat in general relativity. Okay, they're referred to as Kerr black holes. They have a separate metric known as the Kerr metric. And therefore, the non spinning black hole is really a theoretical simplification in order to understand the phenomenon better. Once you understand a non spinning black hole, you can then try to understand a more complicated spinning black hole. But supermassive black holes are all spinning. Is it definite or random each time? It depends on each galaxy. What is the angular momentum of the galaxy itself? So, for example, our Milky Way galaxy is a rotating disk. Okay, it has a certain angular momentum, and it has a certain direction for the angular momentum vector. So there is a definite direction, but that direction need not be the same for all galaxies. It could be aligned in different directions in different galaxies. Are the
Yes.
majority of black holes supermassive or stellar mass? That's easy, because in a galaxy, you have only one supermassive black hole or zero, right? Unless it's a recent merger when you have two black holes which are about to merge, every stable non-merging galaxy will have only one supermassive black hole. It may have thousands or millions of stellar mass black holes. So what is more common? Stellar mass black holes outnumber supermassive black holes by many orders of magnitude. If SO2 orbits so close to the black hole in the center, how has it always escaped its pull? Okay. See, remember, we think of a black hole as enormously massive, but it need not have a enormously strong gravity. And even if it does, so long as you are in a stable orbit, you are not under threat, right? For example, Mercury is going around the sun. It's much closer than the Earth is, but there is no danger that it will fall into the sun, right? And the reason for that is that it is in a very stable orbit around the sun. So the same thing holds for SO2. It's in a stable closed orbit, highly elliptical, but still stable closed orbit around the supermassive black hole. And it comes close, but it is not that close. You can look up the exact speed with which SO2 moves when it is closest to the center of the black hole. I don't remember the number offhand right now, but it's still quite far away from the black hole itself.
Yeah,
So
there
that's
are
why it
two.
doesn't.
Sorry, there are two questions which are related, but because many questions keep coming, I am missing that. But this was one, and there's a related one. I think it was about whether they will live forever or something like that. Now I missed
That
that.
is that is a very good question. Let me try to answer this.
How do they
Supermassive black
lose
hole.
energy was the other question, but I missed where it is.
Yeah,
Yeah.
yeah. No, this is an interesting question. Do black holes live forever? That's for supermassive black holes. The answer is easy. Yes. Okay. The only way they can die is if they merge with another black hole and form a even bigger supermassive black hole. There's no way supermassive black holes can disappear. What Hawking showed through a phenomenon known as Hawking radiation, that there could be some emission of particles from near close to the event horizon of a black hole, and that could basically take out energy from the black hole, and therefore, see, remember, energy and mass are equivalent to each other. If you pull out energy from a black hole in the form of Hawking radiation, you are effectively lowering its mass, and that can lead to a slow decrease in the mass of the black hole. But usually, if the black hole is massive enough, the decrease in mass is so slow. Hawking radiation, remember, is extremely weak. Okay, it's not strong radiation. It takes many times the present lifetime of a universe for a black hole to evaporate off, right? But this is for a stellar mass black holes. You can also form sort of miniature black holes in large particle detectors. And very often people get really afraid. There was some uh, wrong information circulating when the Large Hadron Collider was turned on that will generate some black holes that will cause trouble. Those are miniature black holes. Okay. Those can actually produce enough Hawking radiation to actually evaporate away. So they can disappear. So even if black holes get produced in the Large Hadron Collider, they're so small that they disappear, and they don't cause any harm to anyone. Whereas stellar mass black holes will take a long time, but also essentially forever. And supermassive black holes, of course, are much more massive and take a much longer time to evaporate away, and so they essentially live forever. Is dark matter and dark energy related to black hole in any way? Yes, certainly. I mean, black hole uh, could be composed of dark matter, for example, because remember, dark matter is something that does not manifest as light, okay, but does manifest itself as through its gravity, and that is something that may be happening. So when you form a black hole, the black hole does not really care whether you are giving it baryonic matter or dark matter. So long as you can squeeze the matter into the Schwarzschild radius, the matter may have any origin at all, it will form a black hole. So there is definitely a connection between dark matter and black hole. Okay, is there a connection between dark energy and black holes? Maybe, maybe not, because what happens at the close to the Schwarzschild radius of the black hole, just outside it, that very, very strange phenomena of physics which we don't encounter normally play themselves out. And if these are related to an explanation for dark energy, then there could be a dark energy connection. But there isn't a direct connection like there is for dark matter.
Okay, I'm flashing other questions, but you do take a call when we maybe pause and go for the next session to answer. Shall I put a
Yes,
couple of
sure. But I think if people are online and they're still listening, I think it's
Yes,
worthwhile. I can certainly go on for another 15 minutes or so.
okay, okay. So, this is the next question. Uh,
Yes. This is a very nice question. How are orbits around black holes predicted? Can they be predicted with complete certainty? So the stellar orbits of SO2 and other stars that I showed you are not predicted orbits. They are just measured orbits. They don't know where the star is going. Okay, they just measure it as it goes along. And once they have enough data points, they can, of course, try to complete the ellipse and figure out how the star is going to move. Okay, so these are not really predicted orbits in that sense. What was can you flash the question again? I just missed what was the second part. Yeah. Can they be predicted with complete certainty? Yes, once you have enough observations. Suppose SO2, which goes around in 15 years, suppose you observe it for 5 years, okay, you know more or less how it's going to move. Referring to the three body problem, so for the benefit of others, the three body problem refers to a problem that suppose you have two objects going around each other, right? You can predict exactly using analytic equations how they're going to move. But the moment you introduce a third massive body into the problem, it becomes intractable to solve analytically how these objects are going to move. But that's only if you want to do everything analytically. If you agree to do things, solve things numerically, it's not difficult to predict the orbits of all three objects as they move around. So for these stars or for any other complex system where you have multi-body gravitational interactions, the whole problem is simply solved numerically. So of course it is harder to solve, but now with modern day computers and modern day codes, it is not very difficult to solve a multi-body problem just doing it numerically. Okay, why is the study of black holes important? So, as I said, as far as supermassive black holes are concerned, they really tell us a lot about how the universe evolved with time. And by universe, I mean how galaxies evolved with time. Galaxies are the largest bound, not really the largest, but they're the largest unitary structures in the universe. Okay, by understanding how galaxies form and evolve over time, we are able to understand how the universe itself evolved over time. And we need to understand galaxies in a comprehensive way. So for example, we need to understand how their black holes formed and evolved. We need to understand how their stars evolved. We need to understand how their gas changed with time. We need to understand how their dust content changed with time, and so on. Okay, how their dark matter content changed with time, etc. So black holes are one important component of that study. And as I mentioned, since the evolution of the black hole seems to be correlated with the evolution of the bulge component of galaxies, therefore it makes sense to try to study both of them together. Galaxies are not truly moving away from each other at the speed of light, okay? Because the universe is expanding, right? It's expanding everywhere, right? We are not at the center of the universe. We are not in a special place in the universe. So as we look further and further away, we will eventually reach a stage where we can't see the galaxies at all, because they're beyond our observed horizon. Okay, that's the reason we don't see those galaxies, not because they're moving away greater than the speed of light. When does a star orbiting a SMBH start emitting? This is an interesting question. So if you see that most of the discoveries, or essentially all the discoveries so far, have been from gravitational waves from stars that are going around each other. Okay. Now, if there is a star that is going around a black hole, right, it will not, in fact, emit gravitational waves that will be strong enough to be detected. Okay. So, for example, SO2 is not emitting strong enough gravitational waves. Strong gravitational waves get emitted only when the gravitational potential uh, uh, that is felt by these objects is changing very rapidly with time. So even when two black holes are going around each other, only in the last 1 second or few seconds before the merger is the gravitational waves produced have enough amplitude for us to detect them. So you will not be able to detect a star going around a black hole, gravitational waves from it, because its acceleration is simply not enough for you to generate enough amplitude in the gravitational wave signal. What formed first, the black hole at the center of the galaxy, or the galaxy itself collapsed at the center to form the black hole? So, uh, galaxy, whether the black hole formed at the beginning of the galaxy's birth is something that we don't know for sure. But the fact that the size of the bulge is correlated with the size of the galaxy in every galaxy that we see. And we know, for example, for the Milky Way, the bulge has grown over time as the Milky Way assembled. So we know that the Milky Way initially must have had a very small black hole, which then grew over time to the million mass black hole that we see today. Galaxy itself cannot collapse onto the black hole entirely. No, because it's got too much angular momentum. See, you can ask, why doesn't the black hole at the center of our galaxy attract the whole galaxy and suck in the whole galaxy? It doesn't, because the whole galaxy is rotating around the black hole. It's the same reason why the Earth is not falling into the sun. The Earth doesn't fall into the sun directly because it has a certain rotational speed that keeps it in its elliptical orbit around the sun. So the same thing happens for stars, gas, etc., that is going around the black hole. Only stuff that is very close to the black hole falls into the black hole. Yeah, can I have the next one? How much percent we know about black hole? I don't know. I mean, unless you know what is the total knowledge, it's very hard to say what we know. But remember, we've talked about and discussed black holes only for about, I mean, certainly after Einstein's general theory of relativity and the work done in the 1920s and so on. So it's less than 100 years that the field has existed as a theoretical concept. As an observational study, it's about 50, 55 years old. So it's still early days. I think we know a very small fraction of what is there to be known. Is black hole a body or a hole in space-time? Okay, so I think it's better to think of it as a hole in space-time, because it has no dimensions. The black hole itself, like the Earth, has a certain size, right? Black hole has zero size as an object, and therefore it's not correct to think of it as a body. What is the speed of a black hole? Depends on how it's moving. For example, if you have a merger that's about to happen between two black holes, that will move at a very high velocity. The supermassive black hole sitting at the center of the Milky Way is not moving at all. It's at the center of the gravitational potential of the galaxy. But if you have these stellar mass black holes, which are distributed on the disk of the Milky Way, they are going around the center of the galaxy just like the sun is or any other star is. So the speed can vary a lot. This I already answered about the interior of a black hole. We know very little.
Yeah, sorry. This is actually my mouse is also giving me a little trouble. So I'm having a little trouble now. Coming to the, yeah, this one I think we did not put earlier.
Yes. What is the most distant star captured by a black hole? Okay, won't the heat of the star matter? Okay, so there is one aspect which I did not mention is tidal disruption. So what happens is, if you come very close to, if a star comes very close to a black hole, then before it falls in, it doesn't fall in as one individual star going in, the whole star going into the black hole. It's not like that. Because of tidal forces, the star itself gets torn apart. The gas in the star, the plasma in the star just gets ripped apart well before it falls into the black hole. This is known as a tidal disruption event. Okay. And if you have the right telescope, then you can hope to detect it as it falls in. So it doesn't fall in as a unit. What determines the color of a black hole? The black hole has no color. Okay, it has no property. I said it has spin, charge, and mass. Are all supermassive black holes are quasars? Yeah, that's a very interesting question. So the answer to that is no. Uh, it turns out that only about 10% of galaxies, or even less than that, in the universe at the present time are active, right? Which means they have a quasar active galactic nucleus. 90% or more are just sitting quietly. So, not all supermassive black holes manifest as quasars at any given time. But remember, this is not a question that if an object, if a galaxy is a quasar, it's always a quasar. It's not like that. It will be a quasar for some time, then it will switch off. Then some other galaxy may start becoming a quasar. It will switch off and so on. So, it's just like the lights turning on and off. All the lights turn on at night and during the day they switch off. Quasars are like that. If they eat up the material that surrounds them, then they have no food to eat anymore. They go quiet. Then something happens, some more material falls in, they restart and so on. So they're not active all the time.
Okay. Yeah, there is still
Yes,
quite a
your
number of
observation
questions.
of M87 is what is happening 55 million years ago from today, right? That's always the case because these objects are very distant. The speed of light is finite. You see them as they were in the past. So if an object is 55 million light years away, you see it as it was 55 million years in the past. That's correct.
Well, you let
How to calculate the distance of a given galaxy? That's
actually, yeah, you let me know whether we should, because there are still quite a few. And as I said, I have from the beginning, I have about 30 to 40 questions saved in a paint file.
right, right, right. So
So
we
you
could
tell
do
me when
a
we should.
special session, see, but I'm not sure the same people will be able to attend the next time. That's why I want to take as many as possible. So
Although
I
it
think
will
we
be
can go on
there
for another
online.
5 minutes or so and then maybe stop.
Hmm,
So
hmm.
distance of a given galaxy that is calculated using nowadays using what is known as the redshift. So you measure the spectrum of the galaxy, okay. Then you figure out at what speed it is receding from you. And if you know the something known as the Hubble's constant, which tells you what is the speed of rate of expansion of the universe at the present time, and you know some other cosmological parameters, you can calculate the distance to any given galaxy by simply measuring its redshift. So you measure the redshift, use the cosmological parameters, calculate the distance. Yeah. Other, yeah. Surface gravity is very high so that light cannot escape. Uh, is this the case? Then won't the whole universe be eventually small followed up? No, because if you're sufficiently far away from a black hole, it doesn't affect you. It is not sucking you in whatever happens. Because if you're in an orbit, for example, the sun is in a stable orbit around the center of our galaxy, which contains a black hole. It is never going to fall into the black hole. Does the spin of a black hole certainly have? It has something to do with it, how much it ejects. Yes. Okay. Higher the angular momentum, the higher is the mass ejection rate that it will demonstrate. And what its life will be, I already said that for a supermassive black hole, the life is essentially forever. Can we do something to prevent? Of course not, because we are not able to prevent even phenomena around us like global warming. How are we going to prevent any star from becoming a black hole? And why would you even want to? Because uh, it's not causing you any harm, right?
I'm showing this, though you mentioned it, but because I have to stroll
Yes.
up
Do
to
miniature black holes
get
exist?
other.
Yes. For a short period of time, they can exist.
And this question I answered actually, but if you
Yeah.
wanted to
Sun
take it
will
up a
turn
little
into
more.
a white dwarf. Yeah. It will not turn into a black hole or a neutron star. It doesn't have enough mass to become a black hole.
Okay, I think there was this question which I skipped earlier. Yeah, which should.
What is the difference between a neutron star and a black hole? A neutron star is something that is supported by a pressure known as neutron degeneracy pressure, wherein there are no more electrons. There is a soup of neutrons. Okay, the protons themselves and neutrons disappear and form neutrons. And in a neutron star, you basically have a sea of neutrons, okay, which are held away from each other by the neutron degeneracy pressure, which prevents. So there is, I mean, there are equations. There's a whole area of quantum mechanics, okay, Fermi statistics, for example, which explains to you why two neutrons cannot just come together and form a bigger neutron or something else. And that is the pressure, that is that repulsive force which prevents the gravity from crushing it further. But if the mass of the star is too high, right, even neutron degeneracy pressure is insufficient to stop the contraction due to gravity. And when that happens, then there is no other force remaining to stop it. Once you go beyond the capability of neutron degeneracy pressure, there's no hope. Then it becomes a black hole.
Okay, there is this
Now,
and
when the black hole
related
dies
one
and
how. Oh,
vaporizes,
sorry,
where does
sorry.
mass go? It goes in the form of radiation. Remember, mass and energy are. But don't be caught up on this black holes dying. It's not very easy for a black hole to die.
All right. And I think there are a number of questions on and off about quantum tunneling and black holes. They
My
all
God.
went up.
Okay.
I have
Yeah, yeah,
found
yeah.
this
These
out.
are these are very hard for me to understand. Okay, it's even
Uh,
harder for me to explain to you online, and it
I
doesn't benefit the others who know nothing about what's going on.
I
Are all
think
quasars
you took
redshifted?
this up.
Yes,
No, you took
yes.
this up
All
or no?
quasars are redshifted. They're definitely. We live in an expanding universe, so we expect that objects will be moving away from each other. Are there more black holes in a galaxy? Yes, there are millions of stellar mass black holes in the galaxy and one supermassive black hole at the center. Was our Milky Way galaxy once a quasar? Yes, definitely. There is evidence to show from X-ray observations, Fermi bubbles, and things like that. There is evidence to show that our galaxy was definitely a active galaxy at some point in the past. It is not right now, but there is a possibility that in the future it will again become an active galaxy.
Very interesting question has come.
How will a miniature black hole be formed? So, if you have a large particle accelerator, right, things are moving at extremely high energies. They're colliding with each other with extremely high energies. In those circumstances, when you have a large number of particles moving at relativistic speeds, there is a non-zero probability that the conditions will be right, that some matter will be squeezed into its within its Schwarzschild radius and form a miniature black hole. So they can be formed in extreme physical conditions, like in particle accelerators or in astrophysically equivalent situations where you have extremely high speeds, high densities of particles moving at relativistic speeds.
I don't know the context of this.
I don't know what
Huh.
TON 618 is.
Huh. So maybe I may have missed a couple of questions here because there have been so many. If I
Huh,
have missed some in the current one, then maybe
huh,
the participants, you could post it again. I'll now try and get the old ones. But old
okay.
ones, as I said, there are already 30 or 40 of them. Should we do
Yes,
them in the next session?
we can do that. We can do that.
Uh-huh.
Right.
And yeah,
Can
okay.
we
So
make
can
a
we
black
make
hole?
a
Yes,
black hole?
in particle accelerators, but a very small one which doesn't last very long. You can't make a stellar mass black hole.
And yeah, I don't know. Sorry, my mouse is giving me trouble.
Okay.
So I don't know what portal is meant here.
Black holes, as portals, probably they mean wormholes to sort of travel
Oh,
rapidly through space. So that I already answered. You may
oh.
want to read. Kip Thorne has also written a book about the physics behind the movie Interstellar. I forget the title of the book, but you can look it up. Kip Thorne is the author. You can check what it is, and there's very interesting things in there. Why
So,
black hole is a tear in space-time, and at the same time it has mass, spin, and charge. It has mass because it's got infinite density, but doesn't mean it can't have mass. Similarly, it's not a physical object, but it can still have the properties of spin and charge, primarily because these quantities are conserved, right? These are conserved quantities. If you put a charged particle into a black hole, an electron, let's say, it's going to acquire that charge. That charge cannot be created or destroyed. It's going to remain within the black hole.
okay. Yeah, there was this. And Samyak Shinde,
No black
please
hole
repeat
has
this.
ever had an impact influence on the Earth, for sure, not in recent times at least.
So, because it's difficult for me to go up and pinpoint a particular question, Samyak Shinde, you repeat your question here so that I can then easily get hold of it. If I scroll up, it's more difficult for me to find the question you are referring to. I think now this one, yeah. As far as I see, most of the ones which are here are answered. Let me see if he has now asked it fresh. Oh no, Samyak. What happens if we fall into a black hole? I think in some sense.
Oh, that's a very interesting question. What happens? So you should probably read some of the textbooks about black holes, writings by Hawking or Penrose. They're popular books as well. So various things happen. So one of the things that will happen to you as you fall into a black hole is that because of tidal effects, you will get stretched. So suppose you are falling in feet first. Okay. If you're falling in feet first, your feet will feel the gravity stronger than what your head is feeling. So it'll get pulled in faster, right? Your head will remain behind. So what will happen? Your body will get stretched. And more importantly, eventually it'll get torn apart as you come close to the black hole, right? And eventually then your lower torso, upper torso, everything will get torn apart. You will get nicely atomized when you fall into the black hole. Also, the concept of time that we have it, we know that general relativity alters clocks, right? Time as we measure it. That slows down. So for an observer who's looking at you from the outside, as you approach the event horizon, he or she will feel that you are slowing down and nothing is happening. You're not. It's like a movie that is stuck. So all kinds of really crazy phenomena will occur with you. It's very hard for you to actually observe them because of all this tidal effects. You'll probably be dead by the time you get close enough for the really interesting stuff.
Okay, this is just a clarification about the
Oh,
question. He says that
1,618
this
is
is
the
the
largest
largest
black hole.
black
Yes,
hole.
it's the most massive,
Oh,
supermassive black hole that is known at the present time. So these objects are definitely growing, right? Typically, if they're still active, that means they're growing. They're accreting more matter. They are growing in size. Now, whether it matters, whether we can even measure the increase in the mass, that is a much more difficult problem. You're not going to be able to, from let's say 2020 to 2021, the increase in mass will be so small compared to the total mass of ton 618 that you will not be able to measure the increase in mass. But by measuring how much radiation it is putting out, you can even compute what is the likely increase in the mass of the supermassive black hole with time. Which is the nearest black hole to the Earth? We have not yet have any confirmed uh, proof of the existence of black holes within our galaxy. Remember the gravitational wave detections, which showed these merging black holes, were all in other galaxies outside our own,
stellar mass, stellar
quite far
mass,
away.
stellar mass ones.
Stellar mass ones also, there are a few candidates amongst the stars. Okay, but there's no definitive proof. I don't know which is the nearest star which is a likely black hole. What happens when the Schwarzschild radius of a black hole gets smaller than the Planck length? Okay, the Planck length, remember, is such a tiny length that I don't even think it makes any sense to have a Schwarzschild radius that small. because that mass will be so small that it's nothing. So this situation never encountered in nature. Yeah, I've heard that a black hole emits light and radiation whenever something falls into its horizon. That is true. As something goes in, it gets disrupted, it gets heated up, and definitely it emits some radiation before it goes in. So, if let's say a star is getting tidally disrupted and falling into a black hole, it will definitely emit radiation, which we can detect. Can
So,
space-time tears occur due to high strain near? See, space-time, remember, is not a physical thing, that it's not a fabric that can tear. Okay, so you therefore cannot have tears in space-time due to high strain. And the analogy of black hole as a tear in space-time has to be taken with a little bit, with a pinch of salt, because you have to realize that black holes are not, space-time is not some physical fabric that is stretching across everywhere that you are physically cutting in some way. So you don't stretch the analogy too far.
I had asked him to repeat, so this is the question he
Samyak
has
has
typed
sent something.
again.
Is the death of a star under Schwarzschild radius the only way to form a black hole naturally? Or can we observe a black hole which doesn't follow by collapsing of huge star? So, for example, the supermassive black holes may have had nothing to do with the collapsing of stars. Certainly, stellar mass black holes are something we believe formed from collapsing stars, but supermassive black holes may just have formed by matter continuously accreting onto a small region and then forming a supermassive black hole. There is no reason to invoke stars for that. So, the answer to that is yes in case of supermassive black holes.
What should we do? There are still more questions, and the
I don't know
older
if
one.
there are some, if you feel it will get over in 10-15 minutes, then I would prefer
Um,
to go through it, because then it will be one coherent set of
uh,
questions.
uh,
People
I'll,
can
yeah, there is this question, and
how can
meanwhile,
you
I'll
tell a black
also,
hole made from antimatter from a black hole made of matter? Okay, not really.
and
You can't tell, because antimatter has the same gravitational properties as matter. You can't tell at all.
I have three such paint files. When I was just, while you were speaking in the beginning, but not all of them are questions. A lot of people are
Yes.
also just doing chat things. But there are
Yeah.
three such files I have with questions.
Okay.
So, do you think we can manage it
No, so how
today?
many, if there are, let's say 20-30 questions, we can go through them quickly.
Okay. So, okay, some of them probably already been handled later
Answered. If they're
because
answered, we'll just go on.
yeah, because there are about wormholes, etc., etc. Yeah. There, while you were speaking, I think Vibhor Rana has said, "Is it real that black hole mass having 1 billion that of sun?" I can't believe it. That's all. That was just a
Yeah, yeah, it is real.
gimmick.
Don't worry. Yeah.
How are black holes so powerful that even light can't escape? In a way, that has been dealt with to some extent. How are black holes so powerful that even light can't escape? How is so much mass condensed to black hole? Why condensed, and what happened when whole atom condensed? Is that thing which is
Yeah, that I don't understand fully what he means
okay?
by.
I think this question maybe you may want to, because it will then we can you can talk about the M87 observations too. Why is it difficult to photograph black holes when they have bright accretion disks or even quasars that emit a lot of light in UV spectrum? Simply that
Correct.
they are so far away, and
Yeah,
the
they're
stellar
very
ones
far
are not
away,
so
and
bright.
the angular size of the Schwarzschild radius is very, very small. Okay. And if you observe with, even with adaptive optics, whatever technology you have with optical telescopes, you cannot get the angular resolution in the image that you need to see the black hole, right? But with advanced technologies known as very long baseline interferometry, which was used for the Event Horizon Telescope, it becomes possible to obtain angular resolutions that are simply impossible to reach with optical telescopes. So you can do that with high frequency radio waves, which was done exactly for the Event Horizon Telescope. That's why you can't see it. It just
Uh,
washed out by this. There's a tiny black spot, and there is, bright glowing region all around it, how are you going to see that black spot? That's the question.
Is this the one I think you did already? Yeah, this Samyak. Because I
Uh,
saw this
I am
Samyak's
not
question
seeing the
he posted
questions
earlier.
themselves. I'm seeing a screen.
Uh.
It's not
Yeah,
flashing
yeah.
in that large font.
I'll repeat them. Uh, if this is confusing, if gravity is not a force, how can the hydrogen clouds warp the space time to form a star? Oh, okay. If
Gravity is
gravity is
not a force.
not
Gravity
a
is
force, how
definitely a
can
force.
hydrogen clouds warp the space time to form a star? This seems to be one.
You don't have to warp. I mean, you do warp space time. Everything when we exist, we warp the space time around us. Every massive object warps it to some extent. But
Cha-
gravity is definitely a force. There is no problem with that.
Charu was asking whether by shrinking of a planet a black hole could be formed. And then let me open my
if
second file.
you if you
Yes,
create
yes,
if
yes.
you have some technology by which you can squeeze the earth to a size of a grape, you will form a black hole. But currently on earth we don't have any such technology, so it's not theoretically impossible to convert planets into black holes, but it won't happen naturally.
Right in the beginning, Unnati had asked this, and probably, I mean, we may talk a little bit about how stellar mass black holes have been determined to be so. In answer to this question, or was it dealt with when you are talking? How can we learn about black holes if they trap light and can't actually be seen? This is a question which comes many times. You
Yes,
did
I think I
go
tried to
through it in
address
the
that.
yeah,
Yeah.
yeah. You went through it in your session, so probably she asked it even before you came there. Somebody
Yes.
wants to know Nakshatra Jain, what is there at the other side of black hole?
We don't know. There, unfortunately, the black hole is like a one-way street. If you go into the black hole, you can't come out. Okay, so you can't communicate across the event horizon boundary. Okay, so
Okay.
suppose you went inside a black hole and you wanted to send a message to us outside, what it's like inside, it'll never get to us because you'll send a radio signal and it'll never come out.
Hmm. Yeah. And okay, how do scientists calculate the mass of a supermassive black hole?
Yes, I
Again,
thought I had one slide
yeah,
where
yeah.
maybe I didn't
That's what.
spend
So
enough
add it
time.
to your talk. These are questions which came even as you were just talking.
Yes, when I was just starting, yes. So very briefly, by measuring the speed of objects that are going around the black hole, how fast those objects are moving, and the distance from the central object, one can simply use Newton's gravity and Newton's laws of motion, etc., to calculate what is the mass that is at the center.
If two supermassive black holes come in front of each other at angle of 180 degrees, then what happens?
Uh, they remember they will have some angular momentum, so they will start circling each other, and due to friction they will lose energy, and they'll come closer and closer and closer, and eventually they'll merge. That is what I tried to show in that simulation of a black hole merger.
Anishka and Unnati, your questions have been answered. So Unnati wanting to know if sun would turn into black hole, and Anishka asking whether black hole and neutron stars are the same. These have been answered. Uh, okay, this is one more file I have. Okay, many of these have also come later. So, okay, I see that these have come out later. Somebody wants to know whether there are millions of black holes in a galaxy.
Yes, yes, that answer is true. Yes.
Okay, most of these I see they were repeated later. Uh, Somebody said, "My, if we know all about black hole, then what we do? Make black hole, identify black hole, or only observe from thousands of million light year? In general, we are only observing them.
Yes, that is the nature of astronomy. Remember, unlike other branches of physics, where you can do a controlled experiment, okay, like in whatever particle physics or condensed matter physics and so on, you can do a controlled experiment. In astronomy, the distances are so large that we are in no position to actually tweak anything. We can't change, for example, we can't change the mass of the sun or something. It's there, it's a given. So what we do is that we observe many, many different objects in every class. So if you're studying stars, you observe stars of different ages, different masses, different surface temperatures, and so on, and then try to figure out how they evolve. There is no possibility of you changing. I want the sun to, instead of being a G-type yellow star, I want it to be a red giant tomorrow. You can't do that, right? So it's all observational. That's why we say observational astronomy rather than experimental astronomy.
While you were presenting at that time, Gitanjali Sethi was mentioning that one is using a virial theorem to estimate. Is it really a virialized system?
Yes, so there are many reasons to believe that it is a completely relaxed virialized system. Okay, and you can do tests, experimental or observational tests to verify that it's virialized. Okay, it may not be completely virialized, therefore the virial theorem may not be 100% applicable. You may make some small error in your computation, but it's not wildly wrong. Definitely.
Ritvik was asking whether there are any projects which undergraduates could take up in this.
Mm, See, what, like, I personally have this problem that if you want to do things at the threshold of research, okay, then it becomes very difficult because you have to do undergo a lot of training, because these research projects are typically done by PhD students who have had right lot of training up to their master's level, and then a lot of graduate school training in our astronomy programs and so on, before they can do valuable research. But what is would be very useful if you want to do a project is to try and either try to do an online course, and through EDX, Coursera, etc. There are a lot of options now available uh, to prepare yourself for that. And the second thing is you can do is there's a lot of reading material that is available online. So one can do that and prepare yourself. Then if you find that something is really exciting, interesting, you want to make a career out of it, that is the time to try and do research projects, because otherwise those research projects are not very useful to you because you don't understand much of what is going on, right? And they are not at all useful for people like me because I have to spend a lot of energy to explain the basics to you, and at the end of it you're here for 2 months, 3 months, then you move on to another project, and you may have learned a lot, but we have not gained much from the interaction. Therefore, I strongly recommend to students that don't even try to do projects directly with people. Okay, you first prepare yourself for a research project by undergoing courses, reading books, solving textbook problems, etc. And then once you do that, you are ready. If you want, then if you say if you want to do a career in astrophysics, then I say by all means please come. And then if you're selected in our program, there are many astronomical institutes within the country now. The IITs, ISERs also have opened astronomy research departments. There are plenty of emerging opportunities for you to do research. But just a very short introductory project is something that becomes very hard for most astronomers to support.
I've
Can a
started
black hole
flashing
become
again because
anything bigger than the black hole itself? Of course, why not? Right? Black hole is always hungry. Can Earth encounter any rogue black hole? Extremely unlikely, because the orbits of stars are are quite stable, and the separation, the average distance between two stars, is very, very large. So it is very, very unlikely that any rogue black hole will encounter either the Earth or the solar system, etc., over the short period of time. Of course, rare events, given a million years, even a rare event can occur, but it won't occur in the next 5 years or 50 years. Why don't all quasars show the nebulosity of host galaxies? This is very interesting. This is just an observational effect. This is because the quasar is so bright that it is washing out the light from the rest of the galaxy. So think of a house which has 1,000-watt bulb, and right next to it, it has many 20-watt or 10-watt bulbs, right? You'll only see the 1,000-watt bulb. You won't be able to uh, see the fainter bulbs around it because the light of that will be washed out by this bright bulb. So exactly like that in a quasar, you can't see the host galaxy, but with adaptive optics and sometimes with the Hubble Space Telescope, you can see
Oh,
just a.
I think we did have a good amount of white hole
Concept
discussions.
of a
I
white
still,
hole. What could it?
I miss,
Yeah, I think I'm going to
I,
skip that. Yeah,
and yeah, but there was one question all along. If there are two equal black holes, if they come together, here actually, and among a number of questions, this is there, the second
yeah,
one,
yeah.
and
Two
the
black
first
holes,
one has
equal
already
mass
been
black
discussed.
holes can happily merge with each other to form a black hole with double the mass, double each of their mass. There is no problem.
You don't repeat so many times. Hey, bacha log. Then I'm not able to see other people's questions. If you repeat one question 20 times, we miss so many questions. Now, see, I'm not able to find. Uh, okay, some may have been missed because of all of this, but maybe, I mean, what can be done is once we end this broadcast, as comments to it, if something is left out, what you can
Yes,
do is if your question has not been answered, once this is on YouTube, as a comment to it, you put your question there. Be sure to
right.
put your question there, and that can be. Okay, I see some more which have come in.
Not unfurl the less massive singularity. Um, it doesn't unfurl. What tends to happen is that the two tend to merge. Okay, when the Schwarzschild radii come into contact, there's been a lot of work that has been done, theoretical work on how exactly the merger happens, including many years ago the signal expected signal predicted by Professor Vishweshwara. There are So we know that they merge. There is no real chance of the black holes getting thrown out or pushed back or anything like
Okay, now I'm getting a little confused with new ones coming in. Somebody wants to know why do black holes create black holes? That's not at all
that. They
clear
don't
to
create
me.
other black holes. They can merge with other black holes to form bigger black holes.
Tanmay, was this a point you are making? Was this a question? Maybe it's a point you are making.
Yeah.
Uh, okay, probably then. Mostly, I think I have tried to flash every question. Some may have been left out. As you will see, if you see the comments, you'll see there are so many. I may
Yeah.
have missed here and there. But as I was saying, the
Maybe if
solution
I
for that
may,
will be
maybe in one of the Astro Addas, there could be maybe like a panel kind
ask,
of thing. Maybe you
ask
call
an
three or four
astronomer.
people, somebody
Uh,
on
uh,
stars, somebody on black
uh,
holes,
uh,
somebody on
uh,
galaxies,
uh.
etc. And then let us have a free for all, just a question
Yes, yes.
answer.
Maybe as a follow up to this talk itself, we will have a
Sure.
session where
Yeah.
which will be just
I'll be
asked.
happy to participate
Huh?
in any such session.
Okay, I don't think black holes are also creating wormholes. They're not creating black holes. Okay, so I think we have probably answered everyone. If there was some question which you badly want answered, it wasn't answered, and I missed it, you type it again now in the next 2 minutes. Okay, those of you who are there. If your question was not answered, just type it out quickly now because we will be ending the broadcast soon. So if I missed anything, please type it out. Okay, and this was okay. We got a question.
How small can a black hole get? Okay, that I don't know the exact answer to that question. What the because these would be in the realm of miniature black holes, which I had no understanding of. Okay, so I don't think I can answer this adequately. But there must be from quantum mechanics some limits on how small you can be.
The question which is being repeated about what is the speed needed to escape, so you would have to be moving faster than light, no, to escape. This
Yes,
has
yes,
come up in discussions. And Nakshatra, your question was answered about rogue black holes.
yeah.
Okay, this one, how can black holes have gigantic
Yes.
outflows?
How come black holes
That's
have
nice.
gigantic outflows when they absorb objects? That's a very nice question. See, remember what happens is things when they fall into a black hole, they don't go quietly. Okay. As they circle in and fall into the black hole, okay, due to various effects, they get heated to very high temperatures. Now, when they get heated to very high temperatures, they obviously acquire very high energy. And when they acquire, any particle acquires a very high energy, it starts to move at a very high speed. Okay. So that is what a certain fraction of the particles which are moving very close to the black hole acquire such high energies and such high speeds that they can leave the vicinity of the black hole and come out. Now when they come out, how, why are they directed by jets? And there we believe that magnetic fields play an important role in those, in creating and preserving those collimated jets which drive particles out. Now why are these particles, why are there not larger things like planets or stars coming out? Because of tidal disruption. As by the time you come to the vicinity of a black hole, things are so hot and so disrupted that everything is like a plasma. It's like the sun, right? Inside the sun, if you put the earth, it'll just disappear, melt away. So these are just particles of matter, protons, electrons, and the like, which stream out at very high speeds from those jets. But they stream out because they have very high energy. And that comes from the very high temperature that is created in the vicinity of the black hole. How is time changed in a black hole? Time changes in very, very complex ways in the vicinity of the black hole. General relativity is the theory that you will need to use in order to predict how much of time dilation there will happen. It can be done with either with pure analytical theory or with numerical relativistic simulations to predict how time will. So we understand that it comes out of Einstein's theory of general relativity. Calculated the speed of black holes. Again, this comes mainly from models. So if you, I mean, when they merge together, you know what the gravity is, you know what the masses of the black holes is, you know what their distance is, you know Newton's laws, and therefore you can predict how fast they're going to move. You also know how quickly they're losing energy in their orbit, and therefore you know how quickly they'll speed up and so on. So there are some models and also equations of motion, generally from Newton's theory of gravity, and at later
Uh,
stages from Einstein's theory of gravity.
seems to be something
No, no, I don't
strange.
think
Huh.
you
So, but
can't
this is
create
actually,
something.
yeah, this maybe somewhere somebody came, made some crazy
Ah, okay, okay. This is a very nice
newspaper.
question. Let me try
Uh,
to answer this. Interstellar, if you, those of you who have seen the movie, okay, there they want to go to some planet and do something there, and there they tell you that every hour that you spend here will be like 10 hours on Earth, 10 years on Earth, or something like that, right? That's the reason this astronaut, when he comes back, his young daughter is now an old woman by the time he comes back. Now, that will happen if you have a planet which is in a close orbit around the supermassive black hole, which is exactly what they postulate in the movie Interstellar. That particular planet is very closely orbiting the supermassive black hole, probably in a stable orbit, so it's not disappearing anytime soon. But the gravity of the supermassive black hole is so high, okay, that you are able to dilate time. And those tidal effects that I talked about, close to a supermassive black hole, they're little bit less disruptive because the gradient of the gravitational potential is not as steep as it is for a stellar mass black hole, and therefore you don't get tidal, these astronauts are not tidally ripped apart or anything on that planet, but they do feel, because of the strong gravitational field of that supermassive black hole, which this planet is very close to, time dilates and therefore they lose time. So it's all a complicated concept. Read Kipthon's book to find out more.
I thought maybe we end with this question. I see there's a supernova question later. Maybe we'll take it up in supernova
Yeah,
talks.
yeah.
But this one, Shiva, Under no circumstance, please, neglect your course material, because
Yes.
going through your courses and coming out
Yeah,
with
yeah.
good marks, there is also a necessary step to coming into a research career. But
Yeah, there is.
whatever
Yeah.
your interest
So
is,
in India, the system we follow is that we don't have a separate undergraduate course in astronomy. Okay. Now, whether this is a good thing or a bad thing is a matter of debate. There are pros and cons of both things. Some people feel, yes, we should start undergraduate astronomy. Some people say that there's no need. My personal feeling is that it doesn't make too much of a difference whether you start learning undergraduate or not. What is far more important if you want to do a career in astronomy and astrophysics is to develop a strong background in basic physics and mathematics, because that is the foundation of all of astrophysics. If you don't know basic physics and mathematics, you will not be able to do astronomy. Okay, so that is my advice to you. So if you are studying undergraduate physics, don't, please don't neglect your courses. As Ratnachi ma'am just told you, do your courses properly. If on the side you want to, as extra reading, you want to read some astronomy, do some astronomy courses, etc., please feel free to do so. But you will not succeed in your aim of a career in astrophysics if you neglect the basic physics and maths which you are taught in, let's say, a BSc or a MSc physics course.
questions keep coming. The supernova question Tanmay has answered. There
Ah,
was this one interesting question.
yeah.
Maybe
In
we stop
explaining
after this
stellar
if there
evolution
are no.
involving black hole, whether consider dark matter component. If not, is it not modification required for Chandrasekhar limit? See, dark matter, as far as we know, is not something that is very localized. Okay, so it is not something that you can construct something out of, right? You can just think it of dark matter as a density field that is pervading large areas of space. Okay, don't think of dark matter as an object. Okay, I may not be able to make a dark matter pencil box or something like that. It's not a, it's not, it doesn't interact clearly with matter the way ordinary matter does. So one doesn't need to modify uh, Chandrasekhar limit or any of the equations of stars, because there you, dark matter, even if it exists, okay, it's not going to stay localized. I mean, it may just travel out of the star, or it may come and go. It's not a large fraction of uh, matter where baryonic matter is densely concentrated. You don't. So for example, for calculating the mass of the earth, we don't include dark matter in it, right? Although dark matter particles, maybe they're just passing through the earth and going through in some way.
Questions still keep coming. I'm just flashing here and there randomly some.
There is no center of the
There is no
universe.
center.
The universe has no special place. There is no
And
center.
okay, somebody wants you to recommend some good books for learning. Maybe we close with this. Although here and
Yes.
there a couple of other questions are there, but they may
So
more may
in
come.
the field, I can recommend one nice book for the kind of topics that I have covered today, quasars or black holes, supermassive black holes, particularly. There is a book called Extragalactic Astronomy and Cosmology by Peter Schneider. And I like that book really because it's a very readable book. You can just read it like a novel. If your knowledge of basic physics is good, you will be able to read that whole book like it's like reading a novel. And there are many others. I think you should just browse through or read the reviews on Amazon, etc. And
Uh,
make, because there's so many textbooks, it's difficult for me to recommend anything specific.
so class 10, 11 student, for them some books on astronomy, astrophysics. Probably Frank show
For class
physical
10th, I
interest.
would suggest you read books like Cosmos by Carl Sagan. Okay. If you are interested in black holes and such things, read Brief History of Time by Stephen Hawking. Okay. These are nice basic books. The
Maybe
first 3 minutes, if you are interested in the early universe by Steven Weinberg. But don't get too carried away, because in the urge to sort of leave the mathematics out, they have to explain things using analogies which may not be perfect. So you keep that as a mind in mind. I mean, don't take it totally seriously. And then
Hermione,
later on, you can read more advanced textbooks which have more mathematical and physical treatment.
someone who had asked about color of black hole later on said, "Why are they called black if they don't have color?" And somebody else is also
Black
asking,
means no
"Black
light.
because light is not escaping from them."
Yes,
Okay, I think maybe now we have tackled all the questions. If here and there some things are left, as I said, please put them. Where as we close this, it will come on YouTube, and you can post the remaining questions on that. Shall we close it now at this
sure.
stage? Huh?
Yeah,
Okay.
it was a pleasure
And
to have,
it
especially
was
to have a
wonderful,
very
wonderful. I mean,
interesting
the
question.
way you patiently answered all the questions, and the way there were so many questions. It was
Yes,
very
very happy.
nice, very
Yeah.
nice. So I am ending the broadcast here. Thank you all of you for being there. Be there for the next session for sure. When we will have just for questions. When we'll have a session just for questions. Be sure to be there.